I'm just here to sort of introduce the Stanford Energy Club for those of you who don't know the organization, and then I'll hand it off to Andre, who's going to give you a more focused intro on tonight's event. So the Stanford Energy Club is the largest student-run organization on campus related to all things energy. And a couple of sort of notes that I want to highlight. One, we just launched a new website, so if you haven't checked it out, energyclub.stanford.edu. You can take a look at some of the news that we're starting to post on our website. And we also, the second thing is we just launched the second issue of our journal. So the Stanford Energy Journal, the fall issue we just launched, is focused on natural gas. But more related to tonight's topic, our first issue was on nuclear. So if you have some lingering questions or other thoughts on the topic, we welcome our panelists as well to see our journal. The spring issue from 2012 is all focused on nuclear about 1 year after Fukushima. So Energy-360 is an interdisciplinary panel discussion, and we like to try and get all sides of an issue, whether it's related to business and finance, policy, and technology. And of course, in the past, we've done a few different events on energy storage, on green buildings, on electric vehicles and transportation. And so I'll pass it on to Andre, who can give you more intro on tonight's event, and then pass it on to him.
Thank you, Andy. Good evening, everybody. Thank you all for coming to our event tonight. We've got an exciting topic tonight. We'll be talking about nuclear power with an emphasis on the safety concerns. We chose this topic given recent events with Fukushima, as well as the fact that nuclear power actually holds great promise as a safe, renewable energy source. So we brought in 3 panelists for you all tonight. They're experts in their fields to discuss the potential societal benefits and the safety concerns of nuclear power. Leading our discussion is Professor Leonard Weiss. He is an affiliated scholar at the Stanford Center for International Security and Cooperation. He has served on the National Advisory Board at the Center for Arms Control and Non-Proliferation in Washington, D.C. For 2 decades. He worked with Senator John Glenn as a staff director for the Senate Subcommittee on Energy and Nuclear Proliferation, as well as the Committee on Governmental Affairs. And he was the chief architect of the Nuclear Non-Proliferation Act of 1978, as well as helping to create legislation that created the Defense Nuclear Facilities Safety Board. So in addition, he's published numerous articles on non-proliferation issues in journals such as the Bulletin of Atomic Scientists, Arms Control Today, and Non-Proliferation Review. Thank you all for being here tonight. So following the discussion, as Andy mentioned, we're going to have some Q&A, and we'll have a networking social in Sarah Villanova, which we'll take you all to afterwards. So without further ado, I'll hand it off to Professor Weiss for the discussion.
Thank you very much. My mother couldn't have done any better. Every country in the world, and particularly every industrialized country, is faced with the problem of producing the most flexible form of energy, electricity, from more basic commodities like fossil fuels, oil, gas, and coal, hydro and renewables, solar, wind, biomass, geothermal, wave energy, and so forth, and nuclear. The conversion of each form of energy to electricity carries with it environmental insult, raising questions of public safety and health, but some forms are worse than others. Coal in particular, even after processing into its so-called clean version, is such a burden on environment safety and health that in my view, it should be the goal of every country's nuclear energy program, every country's energy program, to phase out the use of coal for electricity generation and heat. When economically feasible. What should be its replacement in the United States? One answer is natural gas, which the U.S. has in abundance and which is already becoming a major competitor to coal in the production of electricity. According to the Energy Information Administration, coal currently produces 42% of U.S. electricity supply, while natural gas has a market share of 25% and growing. To round out the picture, nuclear produces about 19% of our electrical supply, while hydro and renewables are currently used to produce 13% of our electricity. Each form of energy has its proponents and its critics, and with the rise of global warming and climate change as a public policy issue, it's important to understand as best we can what the various alternatives for energy supply can do for us and to us. The purpose of tonight's forum is to examine one of those alternatives, nuclear energy, which is natural to consider as a substitute for coal, since the operation of reactors produces little to no greenhouse gases. But nuclear has serious environmental, safety, and security issues. With potentially serious impacts on the health of populations. And the question is whether those problems can be mitigated in a way that is politically acceptable and economically affordable compared to nuclear's alternatives. In the wake of Fukushima, Chernobyl, and 3 Mile Island, this forum's title, Nuclear and Peril, in which case the issue becomes how to realize nuclear's promise while minimizing to acceptable levels the peril of nuclear energy in an affordable way. To help us sort out the elements of this important issue, including the use of nuclear waste disposal, we have on hand 3 experts on nuclear energy, and I will now introduce them in the order in which they will speak. The first speaker will be Alex Komorowski. Did I pronounce that correctly?
Yes, it is.
Okay. Alex is Managing Director of Ritchie Capital Management, responsible for venture capital in the Western U.S. He was on the founding team of Honda's corporate venture capital group starting in 2002 in Mountain View, California. Prior to that, he was Managing Director on the founding team of Motorola Ventures, the corporate venture capital arm for Motorola starting in 2000. He spent 17 years in GE in engineering and marketing positions in the Power Systems Nuclear Energy Group before he joined MAC, a management consulting practice in San Diego, California in 1985. He received his undergraduate engineering degree from the U.S. Naval Academy in 1961 and an MBA from the University of Santa Clara in 1971. He has lived and worked in Silicon Valley since 1967. After Alex speaks, the next speaker will be Tom Isaacs, who I've known for many years. Tom works on issues at the intersection of nuclear power, national security, waste management, and public trust and confidence. He's a member of Lawrence Livermore National Laboratory and a visiting scholar at Stanford CSAC Center, where I am also. He is a member of the National Academy of Sciences Board on Nuclear and Radiation Studies. He was the lead advisor to the U.S. Blue Ribbon Commission on America's Nuclear Future. Mr. Isaacs began his career with extended tenures at the Atomic Energy Commission and the Department of Energy. His degrees are in chemical engineering from the University of Pennsylvania and engineering and applied physics from Harvard University. The third speaker will be Dr. Mike Dunn, Director for Laser Fusion Energy at Lawrence Livermore. Before he came to Livermore, Mike was the international project leader for the European Laser Fusion Project, HYPER. He created a consortium of 26 institutions across 10 countries to develop one of the few giga-euro scale facility opportunities accepted onto the European roadmap of future research infrastructures, as well as onto the UK Large Facilities Roadmap. He held the post of director of the UK, spent 10 years at the US Atomic Weapons Establishment. He has served as a visiting professor at Imperial College London, where he obtained his PhD in plasma physics. So we have a very impressive panel of experts on nuclear energy, and with that as an introduction, let me call on Alex to begin.
Thank you. I guess a few things based on my history and experience in the nuclear industry back when it got started right after the war. And that is that, everything, all of the energy source of the universe comes from nuclear energy, atomic energy, I don't know to say it. The creation of the universe, we learned through astrophysics work that came out of a lot of the early radiation studies, created the universe. That, in turn, our sun, which is our closest star, supplies us with our solar energy, which then creates our wind energy. The hot core of the Earth, which is where all the geothermal energy comes from, is also a remnant of the formation of the stars. All of those come out of nuclear energy. So all of the so-called, what we call renewables here today on Earth, all the terrestrial energy sources are really nuclear-based. It was very interesting that we were able to, in the last century, discover how to unleash the binding energy of the nucleus through a bunch of work that was done initially in Europe and then eventually brought over here to the U.S., which led, unfortunately, to the introduction of nuclear energy through a massive weapon. So we've been sort of tainted by that first man-made use of the energy in a practical way with a weapon. And a weapon that is a weapon of, obviously, mass destruction, one of the most feared weapons that man has ever developed. But soon after that, we all, once we saw the destruction that was caused by that, its use in World War II, we then turned to the peaceful uses of energy. And there was a lot of work guided by the United States initially, and I don't know if people remember, some of these gentlemen might, but in the early days, we were going to have nuclear mining. We were going to use nuclear weapons, speed up the whole process of recapturing minerals and so on. We also had nuclear airplanes. We had nuclear rockets. All of these things were actual projects established after the war. The one that turned out to be the most useful in use of energy was the power production side of it. And a lot of different reactor concepts put forth that were experimented with in what are today the national laboratories led to the initial use of the energy in submarines in the U.S. Navy and other ships. It was also put into surface ships. And that's where I came into the picture. When I got out of college, they just set up the nuclear submarine program, and so I got engaged in that, and I actually operated a nuclear power station on board a moving platform submarine for several years in the early part of my career. By that time, we had taken that technology and moved it over into the civilian commercial land-based reactor stations, and there were 3 or 4 major industrial companies that had taken up that technology, and they started to deploy this with the electric utility companies around the U.S. Those were derivative technologies that came off of the initial submarine technology that had been developed earlier. I guess the point I should make, and then I'll stop because we've got more time, is that we are in the very early days. The plants that were built back at that time, there's 104 of them existing today in the U.S. and about 440, I think, worldwide. Those plants are the first generation of this power technology application. They're like Model Ts. They're pretty primitive if you look at what's been evolved and developed since then. We've developed a lot more technology in many, many fields that has contributed to bringing this together into a much more advanced form. And so the plants that are being built today in some countries, we're building a couple here in the U.S. that we're starting, are the next generation, they're actually the 3rd generation or 4th generation, depending on your count, are going to be much better. But when you look at the long history of the Earth, and what we're going to have to do to take care of the 10 billion people that are projected to populate the planet by, let's say, 2050, nobody knows for sure, we're going to have to evolve a much better way to develop this, and we can't continue to burn the fossil fuels. Fossil fuels are like burning our furniture to keep warm. Fossil fuels are hydrocarbon products that can be used to make plastics and fertilizers and medicines, all sorts of things. To be burning that stuff is kind of ought to be the last use that we should look to that. So over the long haul, we're probably in the first 5% of the development of the nuclear power industry. And some of these gentlemen that are working more on the research side will give you some more of a taste of where we're going and some of the future promise that we have for nuclear energy. But to base your analysis of it upon what's been done today in the last 50 years or so is really just kind of a distortion of where things are going to go in the end. It's like the internet early days. Maybe we're 5-10% into the to the use of the internet, but we've seen it just blossom in the last 5 years or so, and it's going to exponentially keep increasing just like that.
Yeah, I should have mentioned earlier, we're going to start off with the panelists giving a sort of a general idea of their view of the problem of nuclear energy and nuclear safety, and then we will get into more detail after they give their opening statement. Tom, go ahead.
Thanks, Tom. So three quick points on the topic here of nuclear safety and what it might mean for the future of nuclear power and how countries are thinking about it in light of Fukushima. And then more broadly, I just want to touch on the Blue Ribbon Commission that I was involved with, because it's a current issue, and I think one that if you're interested in the future of nuclear is very important. So it turns out, being affiliated with CSAC, that just last month we had a meeting with CSAC scholars and Japanese scholars on lessons learned from Fukushima. So it was really timely. And there were a number of papers written both by the US side and the Japanese side. These were sponsored largely by the Japanese government to look into the causes of Fukushima. And what it says is the following. These investigations commonly pointed out three things in assessing responses to the crisis. First, the lack of preparedness, both in core equipment for emergency and in operational capacity of responders and operators, to which confusions in response to meltdowns of reactors and spent fuel pool crises and evacuation of residents were attributed. So that's item number one. Item number two is really interesting to me because I tend to live at the intersection of technology and institutional and social issues. Second, atmosphere of groundless confidence on safety of nuclear facilities which surrounded the stakeholders in nuclear energy, described as, quote, the myth of absolute safety, in Japanese, zetai asnen shinwa, excuse my Japanese, inevitably created situations, quote, beyond the realm of prediction, which they call sotugai. So these were actual terms that they could not imagine certain things happening, and if you can't imagine it, then you don't deal with it. And so, and third, the confusion of command and control in response, which should be attributed to the question of political leadership, including the personal style of the Prime Minister and incompetent regulatory authorities, namely NISA and the NSC. You can see he wasn't pulling any punches in this talk. In short, the atmosphere of the myth of absolute safety created situations beyond the predictions in severe accidents, and the manuals of the implementer, TEPCO, the utility, and the government led to this lack of preparedness because they did not foresee this kind of accident happening. So that's one key issue, is it's not just science and technology. The marriage of science and technology with political issues, with social issues, with value systems are really important in understanding both this technology and other technologies. And one of the other speakers made a really interesting point, which was, you all know what happened at Fukushima, right? There was a big earthquake and then a tsunami, and the tsunami overwhelmed the wall. There's a paper showing that you can correlate the height of the seawall to the size of the nuclear utility in Japan. The larger the utility, the lower the seawall in relation to the reactor and the emergency generators. The idea being that large, therefore influential utilities would have what was called regulatory capture, that they would have so much influence that they could get away with less in the way of safety. Tied to this idea that we don't think about the unthinkable, led to a culture, if you will, that allowed this accident or this disaster to happen. So that's item number one. Item number two, what's that going to mean for the rest of the world? And I just wanted to, all of these quotes I'm going to give you now, I got this month. These are all relevant quotes, okay? China. The pace of nuclear projects will be slower in the next few years as China seeks to allay safety concerns in the wake of Japan's Fukushima crisis, but commitment to the sector remains undimmed. Nuclear power, this is by the head of the Nuclear Energy Development Authority in China. Nuclear power remains an essential component of China's energy strategy, and the industry needs to do more to persuade the public of its virtues. It's not the technology or finance now holding back the sector in China, but the need to gain public acceptance. That's going to be a common theme here if you catch what I'm talking about. So that's item number one. Item number two, what's that going to mean for the rest of the world? And I just wanted to, all of these quotes I'm going to give you now, I got this month. These are all relevant quotes, okay? China. The pace of nuclear projects will be slower in the next few years as China seeks to allay safety concerns in the wake of Japan's Fukushima crisis, but commitment to the sector remains undimmed. Nuclear power, this is by the head of the Nuclear Energy Development Authority in China. Nuclear power remains an essential component of China's energy strategy, and the industry needs to do more to persuade the public of its virtues. It's not the technology or finance now holding back the sector in China, but the need to gain public acceptance. That's going to be a common theme here, if you catch what I'm talking about. Isao Matsumiya, the Japanese government's senior vice minister of industry, recently stated that he is, quote, begging the country's nuclear regulatory authority to give permission to utility companies to restart the reactors. This in light of the fact that Japanese have essentially committed to shutting down their industry over time. The vice chairman's concerns appear to have little to do with safety and everything to do with the utility company's ability to make money. I'm just reading to you various elements that one needs to think about in this. I'm not casting views one way or the other. South Korea's government should resume publishing polls on nuclear safety after a loss of public confidence. The call came as South Korea, whose public is traditionally seen as pro-nuclear, investigated fake safety documents for parts used in nuclear plants that led to the shutdown of 2 of the country's 23 reactors. By the way, I tell you I have consulted or consult for the Japanese and the South Koreans. Just public disclosure. Australia will have to seriously consider nuclear power as an option if there is no breakthrough on baseload clean energy, Energy Minister Martin Ferguson says. If Australia is serious about mitigating the effects of climate change, then nuclear must be on the table. There is no nuclear power, by the way, in Australia. They are one of the 2 largest producers of uranium. So they sell the uranium to the rest of the world to make nuclear power, but they themselves haven't had it. Okay? So nuclear power was not economically competitive and did not have the required community support. So this gives you a flavor of the importance, not just of the technology, not just of the economics, not just of the diversity, which are all very important issues, but of the fact that these issues, particularly with regard to nuclear, and if we have more time in the conversation, we can talk about this, the issue of social acceptance, social license to do these things is extremely important. The third item I want to mention is this Blue Ribbon Commission on America's Nuclear Future. It was commissioned by the President of the United States, Obama, after he made a campaign promise that if he were elected the first time, he would shut down the Yucca Mountain project. I assume most of you have heard something about Yucca Mountain. It was the sole candidate within the United States for the ultimate disposal of high-level waste and spent nuclear fuel, and I worked on that program. I was the guy in charge of siting when we got to Yucca Mountain. I was in the smoke-filled room on Congress the night that they decided to short-circuit the system and just go straight to Yucca Mountain, which was fought for the last 20 years by elected representatives in the state of Nevada. So we had a Blue Ribbon Commission. It was co-chaired by Brent Scowcroft, National Security Advisor to 2 presidents, and Lee Hamilton, who was a former congressman from Indiana and the vice chair of the 9/11 Commission. These are 2 distinguished Americans. We worked for 2 years. I was on the lead advisor to the staff and made a number of recommendations about how this country is going to have to deal with its high-level waste, because we already got the problem. And the first recommendation, we can talk more about the others, is to move to a consent-based process, that we have got to find a different way of approaching this issue, much like is done, by the way, in Scandinavia, now is being done in Canada and other places successfully, where there is an engagement and a serious engagement with society and with the society's elected representatives about how to move forward on issues like this. The marriage of the science and technology that we have, the energy needs, and the social and political fabric that's required to make things go forward is what gets my juices flowing, and that's the kind of thing that I think we need to spend more time understanding if we're going to be successful moving forward. I'll stop there.
And Mike?
Okay, thank you. All right, so I guess I'd like to talk about a somewhat different approach to how you might solve the conundrum that our chairman posed. And that is to use the process directly that the sun and all the stars use, the process of fusion, which is combining hydrogen, the smallest atom, into helium, the next smallest atom. And if you can do that, you don't have the spent nuclear fuel problem for which you need a Yucca Mountain. You don't have the nuclear proliferation problem that you see playing out in Iran and elsewhere. But there is a good reason that the sun is 93 million miles away, and it does give off quite a lot of energy. really want to have that sitting next door to you. You'd have your very own safety problem there, I guess. But it's actually a little known fact that the energy density of the sun is about the same as horse manure. It's not very much, but there's actually a lot of it. And so it gives out a lot of power, a lot of heat. And so the challenge, from my point of view, from the field I come from, is can you reproduce that sun in miniature? In fact, can you make it so small that it only needs about 1 milligrams worth of fuel? And if you can do that, then you have a system in which there's no runaway safety reaction possibility whatsoever, because you're trying as hard as you can to burn all that fuel. And each of us would need about 1 gram of fuel per year for all of your energy needs. There's only one small problem, which is that it's never been shown to work. But that doesn't stop people often. The challenge of how to introduce fusion here on Earth actually started back in the 20s, when a fellow Brit, Sir Arthur Eddington, figured out how the sun works, working with Einstein. And in the 50s, a whole bunch of programs were started to try to harness that energy. But the story really took light here in California in 1960, over in Malibu, when the first laser was produced. And from that point onwards, actually a few days from that point onwards, people thought about using the laser as a source of energy to spark the fusion fuel alight and reproduce in miniature a sun here on Earth. But you have to roll forwards 50 years and a few $1 billion worth of investment to the point at which we now finally have a machine which is big enough and we think capable enough to producing more energy than it takes to spark the fusion process. And in fact, there's been some recent criticism in the press, in the New York Times and elsewhere, that this facility, which is known as the National Ignition Facility, didn't achieve net break-even, net energy production last month. The joke about fusion is it's 50 years away and always will be. The criticism around at the moment is that it wasn't achieved last month. So it feels close. And so my job is to figure out how to get from that demonstration, which we anticipate in the next short period of time, to building a fleet of power plants, and doing so in a way that's publicly acceptable. And in particular, trying to learn the lessons from the first generation experience, as Alex talked about, of nuclear power, and see how we can evolve forward from that. I think there's lessons to be learned, from nuclear, as Tom was saying, in terms of it's probably a failed approach to say we've got a better idea. Trust me, this technology is better than the last technology. It really will be better, honestly. We can learn lessons probably from the medical industry with regards to how technologies like MRI scanning and stem cell research are being rolled out. And fundamentally, it does come down to an issue of public trust and public ownership of the solution, rather than some technological organisation or community trying to impose a solution on the industry. And so, I guess from my point of view, I'd be very interested to discuss and learn lessons about the safety experiences of nuclear, how the public perception can differ from logical analysis of the actuality of risk, and how we can make use of that in introducing what I think is most likely to be the long-term next generation form of nuclear power. And hopefully it's closer than people anticipate. But do so in a way that is responsive to those needs. And I guess, in case I forget to say, given that you're all local,
Thank you. Well, let me, before I turn it over to the audience questions, let me ask a couple of my own based upon what we've heard so far. Both Alex and Mike have referred to the early nuclear plants, and Alex said something about, referred to them as Model T type plants, old plants with old designs that are still operating. Now the Nuclear Regulatory Commission, which is responsible for ensuring that plants are supposed to run safely, has extended the life of many of these reactors by 20 years. Their rated life was 40 years. They have gone through a process of review, and the Nuclear Regulatory Commission is allowing them to run for 60 years. And my question is, well, to anyone who wants to answer this, do you think that this is a risky way of regulating nuclear plants, or should we be accelerating the introduction of new designs?
I think it is a risky way. However, it is, you have to balance the risk against the economics and the cost. And the reality is that if you go out and build a new plant today that's a modern form, not the old style, is a big expense. There's a big front-end capital expense associated with that. Now, the fuel cost is very low, so over the life of the plant, the energy cost is competitive, but you have to put a big upfront expenditure out to build these things. And that's a real impediment to electric utilities who have to raise the funds to build these things. So it's a lot more economic to take an existing plant, even though it's not the latest and greatest, and try to keep the thing running. It's like if you had an old car, you got a 5-year-old car, do you run it 5 more years, or do you trade it in and get a new one? Well, it's the same kind of an issue, but because that's an individual decision, you can, there's a lot of factors involved, but as we were saying here, this is a social, political decision when you build a nuclear power station or any other large power station. There's always this NIMBY problem that people don't want to have a facility, a large facility nearby, one that's got risk associated with it, and every energy producing facility has risk associated with it. So we've got to balance that. And so what they've done, the NRC has done by extending these things 20 years, is put down a strict set of requirements that you have to meet to show that all the major components of the plant will, be able to take the extra duty. And the main component is the reactor vessel. Reactor vessels in large nuclear power stations are like 80 feet high, they're like 20 feet in diameter, they're like 1.5 feet thick. These are huge structures. And at the core belt, where the core sits inside the reactor vessel, there's intense radiation that comes out. Now, there's some shielding by water, and there's some other metal structures inside, but it's a very intense radiation field, all the forms of radiation coming at that thing. And you worry about embrittlement problems in these large steel structures. So you've got to demonstrate that the structure will maintain its integrity over that extra 20 years. But there are a lot of other components in the plant as well that have to be studied. And most everything in the plant can be replaced. So if they're large coolant pumps, you can replace pumps, you can replace floaters, you can replace the whole pump. You replace piping, you replace the fuel automatically every year or so when you refuel the thing, or at least portions of it. So in a way, it's like having your car that you just keep replacing the parts in to keep it going, and the only thing you really have to worry about long term is just the frame's going to hold together. Because at that point, when that breaks or bends or whatever, then it's probably worth starting all over again. So that's the approach they've taken, and it does have risk associated with it, but it's a cost-effective way to keep a 20% nuclear component in our energy mix these days. Without that, if we lost that, then we've got the offsetting problem. We've got to come up with other energy sources, and if you look at fossil fuels or any of the other things, they all have outcomes and risks associated with them that are not desirable.
Yeah, I'll make a couple of comments. I think that personally that the current fleet of nuclear power plants operating in this country today are operating extremely well. The availability of those plants, which in the early days was about in the 60% range, now most of those plants are available and running over 90%. And that's a very good indication that those plants run very, very well. the NRC is the gold standard for regulators around the world. If you want to have a new nuclear plant design in another country, and you want to convince people that that design is really what it needs to be, you go to our NRC and ask to get it certified, because they will be the most thorough and the most rigorous party to independently verify the safety of those plants. So I think there's a lot to be said for the fact that while there is always residual risk, the biggest risk is complacency. It goes back to that thing I talked about in Fukushima, where people say, oh, this can't possibly happen, so I'm not going to worry about it. It's that, or this has never happened before, so I don't have to be concerned. When you get complacent with almost anything in life, that's when accidents happen. That's when there are problems, is when you think somehow now I understand it. So I don't have to really focus on it. But I personally think when we look at the array of options in this country, that nuclear power is an important element of a diverse energy future. Because the one thing we always find, at least throughout my career, is we're always surprised by what happens on the energy front. We think we know what's going to happen, and then there's an oil crisis, or there's an accident of some sort. So the world throws surprises at us. We're lucky. We're lucky because we've got lots of various resources. We have lots of gas, we have lots of coal. You look at Japan and South Korea as examples of energy-intense countries who have essentially no indigenous resources. So they need to look to options like nuclear power even more than we do. So I think to answer your question, Len, going from 40 years to 60 years was a methodical decision by the regulator. The industry had to make very, very in-depth analyses and convince folks that it makes sense. There's always residual risk. That doesn't mean that the fact that there's residual risk makes it unacceptable. But in my view, I would say that the future of nuclear power in this country is probably not very bright for the coming years, mostly based on the fact that there's lots of cheap natural gas, and as was stated by Alex, the upfront cost for building a nuclear power plant, the capital cost to actually build it, are really high. So it's unlikely that utilities are going to build lots of these plants as long as they can continue to buy gas cheap. And we'll see how long that lasts, because gas has this fracking issue now, which is just beginning to be socialized, and we'll have to see how acceptable that is as well. So I think there's a number of issues here, but in my view, it's an important part of the energy future. And the other element, if I can just say, I think it's really important for the U.S. to stay in this business, because I gave you some examples, but there are dozens of countries who are either doing nuclear power, starting nuclear power, or contemplating nuclear power. And the way in which we can influence it, because it's really important to all of us, that their nuclear power plants be safe. We saw what the implications are for Chernobyl, for example, and Fukushima. It's really important to us that they be safe and they be run in ways that national security isn't undermined. And the way for us to do that is to be in that game. I think we've got to be part of that discussion, and the way to do that is to be involved in that technology.
I'll just add one thing, maybe. Yes. So, I do agree that the economic driver for the life extension is very compelling, probably for two reasons. Once you've amortized the capital, the cost of the electricity produced is incredibly low. And secondly, as Tom was alluding to, the economics work well if you have high availability, and the high availability comes with having a high degree of safety assurance from the regulator, seeing up down for long periods of time. So I think it is inevitable that the life extension program has that very strong economic drive and will happen. But it's almost not the issue, I think. If you look at the retirement curve, as you were alluding to earlier, of the coal plants, and even with life extension, the nuclear plants, there's a very, very dramatic recapitalization requirement in the industry that takes off in about the 2030s and goes screamingly upwards in the 40s and 50s, such that hundreds of gigawatts worth of new power will need to be put onto the grid in that period. So whether we life extend or not, we have to address the issue, as you alluded to earlier. What do we build? Is it going to be coal? Can only be gas for so long and for such an amount? So how do we tackle the issue of whether to build big nuclear, even with the huge capital economic consequences? Can we make fusion work in a timely way that is part of the mix or not? So it's a marginal question to some degree, I think, because we have to tackle the issue of how to do new build in some form or other, if you believe that emissions, both locally and globally, are an issue to deal with, which I do very much.
Well, Tom's point about complacency is really an important one. So I want to ask a question related to that. There is a plant that is located, nuclear plant that is located 45 miles from New York City, called Indian Point. It is a very old plant. It is, if an accident were to occur at this plant and an evacuation of New York City were to be tried, nobody believes that it would work. So this brings up also the NIMBY issue, because people in New York do not want this plant to continue operating, and yet the Nuclear Regulatory Commission has so far not shut it down. Is this an example of some sort of American complacency about the fact that you could have an accident of that kind that could have such a wide effect? Because I think it is certainly true, as Tom said. I'll put it in different words, but it's the same thought. A nuclear accident anywhere is a nuclear accident everywhere, because whatever happens in one place with nuclear has reverberations that occur everywhere else where nuclear power exists, which is one of the reasons why you have a Chernobyl accident, and then you have people who don't want nuclear power in many other places which are nowhere near Chernobyl. So, and the same is happening now with Fukushima. So, how are the regulators taking this sort of thing into account in terms of making decisions about what plants should be open, what plants should be closed, what plants should have their lives extended, and so forth?
You know, one of the approaches here, and I mentioned there are a couple of new plants being built in this country, the new generation plants, these multi-billion-dollar facilities, but both of them are being built right now, are being built on the same sites as existing plants. So we're trying to find, you're raising the issue of the plant siting and finding a location. By the way, Con Edison was one of my customers when I was at GE, and they had a proposal for what was called N4, and a plant was going to be built in Manhattan on the Hudson River on the Manhattan side, and we had designs laid out and so on for that. And so if you think Indian Point's a problem, you can imagine if we built this, it was going to be a 1,000 megawatt station, and probably would have multiple units, so two or three units like Indian Point does, and it had been right there in Manhattan. And if that thing, of course we had all the provisions to protect the public, but you can imagine if the thing had gone up in smoke like Chernobyl did, it could have been a serious issue. Fortunately, so the light didn't go ahead with that. But and Indian Point, I think is probably a safe site, and I know people are spooked and whatever. And those reactors are pretty good operating reactors, and so on. They've had good history. Con Ed's a pretty good utility. In the early days, one of the problems with these new plants, the current plants that are operating today, is that the utilities really were not well schooled in how to operate nuclear power plants. They were used to operating big coal stations, maybe an oil station or a natural gas station, or a hydro plant, and they took operators from those plants and put them into nuclear stations and tried to operate them. And that was just, that was part of the reason these things ran at 60%, as Tom was alluding to in the early days. They were very, very poorly operated, and frankly, some of the safety issues and so on involved, I visited a number of these plants, kind of spooked me. And one of the things that Admiral Rickover did when he set up the nuclear program in the Navy was to make sure that safety was the highest priority. And that meant that quality control and all of the fabrication, all the design work, everything that was done had to be absolutely perfected, double-checked, and best it could be. And so the operations, the training of all the operators, everything was done to a very, very high standard. And when I came from that program, where I had been an operator and saw how the utilities operated these things, I frankly was kind of floored. I'm surprised we didn't have, something happen more serious than it did in those early days. But today, the utilities have upgraded. They've actually brought the Navy people in through an organization called INPO, and they've upgraded all the operations of the plants. And so the plants are operating very safely today, much more safely than they ever have. We've got very skilled people running them. One point I wanted to make, Tom mentioned that we've got to be the lead. The U.S. has got to be the lead because we have the technology experience longer than anybody else in the nuclear power industry, and it's true. And he mentioned the Chernobyl thing versus the Fukushima thing. Fukushima is a U.S. reactor. That's one of ours, which happens to be located in Japan, on the coast of Japan. I was one of the engineers involved in building that reactor. So it followed all of the U.S. regulatory requirements, and we basically taught the regulators how to regulate it, and we taught the utilities how to design it or operate it after we designed it and built it for them. And the next bunch of reactors that Japan built like that. And one of the reasons I think they have this complacency that was alluded to in this report is that, Americans, we dropped the bomb, we won the war, we were the gods of the world in technology and so on. So anything that Americans did, the Japanese bowed and they loved us. I worked with the Japanese for many, many years. And they had great, great respect for American technology, to the point where they just assumed that nothing could ever go wrong. Now, the piece that went wrong with Fukushima is not the power plant itself. It was the environmental thing. It's the location of it on a coastline where a tsunami of that size could come in and destroy the plant. And that was never anticipated. They've had some tsunamis in Japan for centuries. But nobody ever expected one to be that close to shore and generate that massive a set of waves. And that's what wiped out that whole Tohoku region, which is where these plants were located. By the way, there were a number of plants that survived this tsunami in that same region and came out fine. Didn't even shut down. Nuclear plants didn't even shut down. So Chernobyl, on the other hand, is not American technology. And so this is where Tom's lesson really, really becomes important. If you do not use the core American technology to develop your programs and our more advanced technology, you're going to have some serious issues. And Chernobyl is far and away the most serious nuclear accident that ever could be contemplated by any nuclear engineer, nuclear utility, anybody. That was a very, very terrible, serious thing. And it was because they didn't design the plant with any of the safety features that we have as minimum requirements in the West. So when you build a nuclear power plant, we have layers and layers of defense, so that if this one goes wrong, that one will back it up. And if that one goes wrong, there's another one to back that up. And everything has got, there's multiple containments before any radiation could escape from that plant, no matter how many foul-ups and things go wrong. And the worst thing we ever had in this country was the 3 Mile Island accident, which you may remember, which turned out to be a non-event as far as public hazard. Now, there was public fear. There was a huge spooking of the public, and people went crazy. But the actual radiation damage to the public or any safety hazard was zero. It was a huge economic disaster. The utility lost millions and millions and millions on that power plant. They lost the use of the power plant, plus they had to spend billions cleaning this thing up and getting it taken care of. So it was a huge economic, financial disaster, but it was not a safety problem. Chernobyl was a complete opposite. It was a huge, huge safety issue, and will never, even the Soviet or the Russians today recognize that they would never, ever build a reactor like that again. That whole class of reactors they built without any containments on them, primary or second containments, that's gone. They've accepted our standard, and that's where this point Tom was making is really important. We've got to remain the technology leaders in this field to make sure that safety across the globe is maintained over time.
Tom, you mentioned that social acceptability is very important for the nuclear business. Could you say something about what needs to be done, in your view, to raise the social acceptability of nuclear power?
Sure, thanks. First, let me, the commercial message, if any of you are interested in this dimension of things, I highly recommend that you get a copy. It's online, and you can get copies of this Blue Ribbon Commission report on America's nuclear future. It was published January of this year, and it talks about this very issue in great detail. One sentence: listen, don't lecture. If you want to gain acceptance, if you want to get public trust and confidence, I often do this with classes. I say, let's do a little experiment. Okay? Try and think of 2 or 3 people that you have a lot of trust and confidence in. Right, do it right now. Who do you have? Not your mother or your brother, but could be the policeman on the corner, could be your elected representative, God forbid. It could be any, who do you have? Could be Alex Smith, or I don't know, Andrew Luck. Who do you have confidence in? And then ask yourself, why are you confident? Why do you have trust and confidence in that person? And when we have a discussion, and we don't have quite enough time today, it usually comes down to 3 things. And they're the same 3 things for why you have trust and confidence in whoever you're thinking of right now, and why you have trust and confidence in these broader issues. The first one is that you believe the person is competent to do what you want them to do, and that they have a track record of competence. I get on airplanes all the time. I put my life, and so do you, in the hands of people you never even met, right? Why are you willing to do that? Because you believe there's a competence to the people who were associated with designing that airplane, building that airplane, flying that airplane, air controllers, regulatory authority. All of that leads to a sense of trust and confidence. But that's not enough. The second thing is that you have trust and confidence because you believe when that person goes to make a decision, they make that decision with your best interests at heart. You're not going to get on that airplane if you don't think that pilot has your best interest, if they're not aligned with you, right? So you want to have that sense that when people make decisions on things that you care about, that they're aligned with yours. If you think they're out to maximize their profit at your expense, you're not going to have confidence, no matter how competent you think they are. And the third one, and this goes to the heart of the question, is you listen. You actually proactively try to, the people you have confidence, proactively try and understand where you're coming from. And they take your concerns seriously. And they don't say, look, I'm a scientist, trust me, I know what I'm doing. They don't do that. If you have a concern, they have a concern. And they want to work with you to try and resolve that issue. And those are the 3 things, and it's interesting, because I've done this many, many times. Those tend to be the 3 things that in one formulation or another tend to cause us to have trust and confidence in people. And that gets translated in a variety of different ways in programs, and the best examples of this are Finland and Sweden, who have by far the most advanced nuclear programs for disposing of nuclear waste. You would think Finland and Sweden, why would they be? Partially it's their culture of the countries themselves, and I won't go into the great details about it, but those kinds of things are very evident in those countries, that they care dramatically, because most of the country are small, isolated places, right? I mean, you have Stockholm and you have Helsinki, but most of the countries reside in small, isolated places where people really have to rely on one another in order to survive. And you feel that when you're in those places, because I've been in those places. And that sense of understanding each other's concern and wanting to deal with it collaboratively and collegially is intrinsic in their way of doing business. And so that translates into a sense of confidence and trust that has allowed them to move forward. And we need to do the same kind of thing in this country. It's not easy, it's not fast, it's tough, but it tends to work. And I've been working with the Canadians. You heard Len's lead in. Their program 10, 15 years ago was just about where ours is today on nuclear waste management. They had stopped, come to a dead stop. They had a very fine technical program. It was stopped politically. The organization responsible for it was taken apart. A new law was passed in 2002, and they started all over again, and they were lucky enough to have some really far-sighted, competent people put in charge of that program, and they adopted this engagement strategy and civil discourse throughout Canada as an essential part of how they were going to put their program back together again. And they took the time, I call it go slow to go fast. All right? They took the time to engage the citizens. The first thing they did was to ask people, what are you concerned about? Not to tell them this is what we're going to do. To say, tell us what you're concerned about so we can try and put our program together in a way to respond directly to your concern. So that's a short, long-winded answer to the question of some of the things that one needs to think about.
Yeah, I'll just build on that a little bit. I mean, which is an issue of scale and the mutuality. When we get on an aircraft, it's a personal decision, isn't it? We don't have to rely on other people making that decision for us. And even when it comes to waste disposal of spent nuclear fuel, all you have to do with inverted commas is convince a community or a small number of communities to build their own Yucca Mountain or theological disposal facility. When it comes to power production, you've got to do that hundreds and hundreds of times in any given country around the world. And so the nature of the conversation about confidence and public trust is at a different level. And I don't think we've quite addressed that yet. There are other examples in society, aren't there, where we've taken on board significant risks and expenditure, but done so because we think there's a greater peril or a greater threat. Building nuclear weapons would be one of those. There was a fear factor put up, whether it was real or not, one can debate. That drove that whole program of massive, multi-billion-dollar investment in what is essentially a very dangerous enterprise. But do so because we think there's something that's even more fearful and we're acting against. When it comes to power production, the conversation is so confused in most people's minds, in fact probably everybody's minds. It's difficult to have that rational conversation. So I'm not saying I'm not heading towards an answer here. I'm not saying there's an answer. I'm saying it's at a different scale of problem that we have to appreciate both at a policy level, and I agree with you entirely. But it is more than just that simple community-focused consultation.
Well, we've come to the point here where it's appropriate, I think, to ask all of you if you have any questions for the panel, to raise your hand, and we will call on you.
This is a fusion question. So you talked about laser fusion at NIF. So this is a two-part question. One, what is your opinion on magnetic fusion as is being done in Europe, for instance, the ITER project that's going to happen soon? And what is your opinion as fusion-fission hybrids as a technology that breaches the gap between fusion and fission and that can be beneficial?
Thanks for the question. I'll try and be brief. So back in the 50s, 50s and 60s, people looked at two essential approaches to fusion, as you alluded to. One, can you use a laser to compress a very small amount of fuel, a little bit like an engine piston, spark it, and it gives off energy, and you repeat at 1,000 RPM to get 1,000 megawatts. And as you say, there's a different approach, which is to take quite a large amount of fuel and heat it up to very high temperatures, overcome the nuclear forces and get energy out that way. And actually, when Reagan and Gorbachev met in Reykjavik and decided that they couldn't solve the world's nuclear weapons problems, they tried to find a problem that they could work together on. And they decided nuclear fusion was sufficiently benign, long-term, and non-threatening that they chose that and launched the project, which subsequently became known as ITER, which is now being built in the south of France, in Cadarache, in Provence. Wonderful place to visit. I recommend a field trip. But that truly is a long-term program. It's about a $25 billion program. It started construction about a year ago. And don't forget, Reagan and Gorbachev started this out. So that was a fair old time ago, 20 years ago. So it took about 20 years to solve the politics of how to get about half of the world's population's governments together to run a project. They had to invent their own currency, and appoint a diplomat, an ambassador, as their project leader. Yeah, 2 warning signs for any project, I would say, when you have to. But finally the construction has started, and the machine's due to come online at the end of the decade and start full operations at the end of the 20s, 2028, 2029. And who knows, I mean, that may well be a robust approach to making fusion energy. Because of a dual use in the defense programs, the laser approach has received much more investment more recently. And the facility turned on 3 years ago that is of the same equivalent scale. So we think there's about a 20-year difference, which if you take the long view, is no difference at all. You know, both are likely to progress. If you take the short-term view of how to get to the market fast enough, we think there's a significant edge. And a significant edge here, not just in the US, but here in California. So we shall see. With fusion, you always have to take the long view at some level. I'm sorry, and the hybrids. So people take 2 views of hybrids. It's either the best of both worlds or the worst of both worlds. Now the program I come from actually started out as a hybrid concept, and about 2 milliseconds after we started talking to the utility chief executives, it stopped becoming a hybrid. And that was for the reason of licensability, the issue I talked about before. That in principle, as a physicist or an engineer, it looks like a really good idea. You get a lot of energy for free, essentially, by putting a fission blanket on a fusion system. What could possibly go wrong? And what can go wrong is that it comes to be a very difficult proposal as to how to license that in a robust way, in a way that takes care of every unforeseen and foreseen eventuality. And so you end up with the same problem that big nuclear has. You've got multi-billion-dollar investment and a licensing process that is very hard to predict when it will end and how much it will cost. If you take away that fission blanket, you have a fusion system that has just doesn't have those problems of the safety or hopefully the public acceptability or the waste. And so you can progress to market that much faster, if you can make it work. And that's the big if. And then we shall see whether the laser approach can get there in the next year or so, whether the fusion ITER program can get there after that. And progress from there. Good question.
Yes.
Is there a concern with lack of human resources and institutional knowledge over time with people to operate these plants and build these plants nationally and internationally, given that it seems like most of our plants are several decades old?
Yeah, there is a lot of the engineers that designed the plants, the first generation, have all retired, moved out. A lot of all the early R&D people are long gone. So there is a active recruiting activity in the U.S. To entice people to come into nuclear engineering programs and join in the nuclear utility industry, power industry. The American Nuclear Society now sponsors a number of these things along with DOE and other players. So that is a concern about getting enough technical expertise and both the design and the operations and construction side to be able to sustain the industry. Right now, there isn't enough of an industry to, have a great need, but if we start building a lot of plants again, we're going to have a problem.
Yeah, I just want to add, I think you're exactly right, and that's a great question. A little over a decade ago, I got asked to chair an international panel looking at the status of education and training in the nuclear field. 17 countries were involved. Chinese and Russians weren't, but pretty much everybody else who was in the business was part of it. And we did extensive surveys. We sent out questionnaires to universities and industry and all those folks, and we came to the conclusion that with the exception of one country, France, every other country in the world was in deep trouble with regard to its infrastructure and its competence going forward. In the U.S., we lost half of our nuclear engineering departments in the country. We lost half of our research reactors in the country. And it's what I call the rabbit and the snake. When the business first got going, it was very exciting, and people of my generation got attracted to it. When I started my work, it was nuclear was the highest energy R&D program in the United States, officially, by the U.S. government. But what happened was, for all the kinds of reasons we've been talking about, that kind of diminished, and we saw that departments, not just the number of departments, but the size of departments was diminishing, and the quality of students were diminishing by a various set of factors that we tried to assess. That got turned around a bit right after we published that report. It got turned around in the US and to some extent in other countries because it looked like nuclear power was going to make a comeback, and that attracts students, it attracts young faculty, it attracts R&D money. All those things are the lifeblood of the future. And so there was a feeling of optimism, and I think there still is, because there are a lot of things out there, we've touched on some of them today, that aren't just about running current nuclear power plants. These exciting things that you asked about, the need to deal. I mean, believe it or not, one of the most exciting things you can deal with is trying to figure out how to deal with nuclear waste. It touches on everything. It touches on, cutting edge science, technology, sociology, psychology, occasionally psychiatry. I mean, it's really spiritual because it lasts forever. It really is an amazing thing, and we attract multidisciplinary students and faculty into these things more and more now. And you see, so I think there's an optimism, but there's no question that it's not a given in this country and in other countries. And if you don't have it, then maintaining that expertise for the future becomes a real risk.
What else?
I have a question about fusion. So when it's kind of looking ahead, when we get to the scale, when fusion technology become practical and large enough, like to solve our problem, I wonder at that time whether safety issue will be also a concern, just like fission, or even bigger, or our technology will be so advanced that we already have confidence in that.
Yeah.
So it won't be a concern.
The safety issue is one of the key attractors that have driven people to work on fusion for these past few decades. Because you only have a tiny amount of fuel in the system at a time, and you're trying as hard as you can to make it burn. You can't be burning, of course, but trying as hard as you can to make it burn. The worst that you can do is burn less than you hoped for, rather than burn more. So if there is an unforeseen event, whether it be an earthquake or man-made event or whatever it may be, the power output would stop rather than continue going as with a fission system. So you don't have this latent heat issue, this residual heat issue that we talked about. So there is that inherent attractiveness there. The key issue is one of the likely fuel has two components. One which is very benign, you find it in water, deuterium. The other is tritium, which is a radioactive substance you have to make. And so the key issue is, can you beat down the inventory of tritium, the amount of tritium in your system, to a low enough level that even if it were all released, there wouldn't be a safety consequence. And we don't know whether the answer to that is yes or no. We think with our current designs, the answer is yes, but we will only truly know when we build these systems and go through that technology development. We think at the moment, if all the tritium were released, there would be no need for public action whatsoever. But we do have to go through that process of proving that. In the far future, maybe you can get rid of that tritium, but it is the key residual safety issue to deal with.
Mike, let me inject something here. What is the level of your confidence, your personal confidence, that a fusion machine will be built within, say, the next 20 years or something like that, that is viable economically and will be bought by a utility for the production of electricity?
Is this being recorded? So there's one big uncertainty, and the uncertainty is the scientific uncertainty. Can you sufficiently control, in our case, the laser system, to start the fusion reaction to the point where you get more energy out of it? And we fundamentally don't know the answer to that. It's the reason the National Fission Facility was built. It's the program of work that's been underway for the past 3 years. Had hoped to be there last month as advertised, but not there yet. And it is inherently an unpredictable event as to whether that will happen or not. It is a leading edge scientific event. But if it is, and we have reasonable expectation based on the science results so far that it could be achieved in the very near future, in the next year or thereabouts, if it is achieved, then the pathway from that demonstration to building a power plant I do think is very short. You know, the characteristics of fusion are just so profoundly impactful to our society, whether it be at the safety level, whether it be in terms of both global and local emissions, whether it be in terms of energy security because of locally sourced fuel, or whether it be in terms of base load, non-intermittent power supply. The challenge is, can you show that it works at scale? And the at-scale demonstration is what we're currently working on. It is the culmination of 50 years' work, but it's not quite there yet. But it doesn't feel like it's another 50 years nor another decade. It does feel close enough that we will know one way or the other in the next year or so. In which case you either will never hear from our community again.
Oh, it sounds like pretty exciting.
It is the time to be around. I can tell you, 20 years ago, there just wasn't anything, and hopefully in 20 years' time we'll be seeing these things built around us. Now, give or take 5 years, backwards and forwards, is just the most exciting time to be around. I think truly, coming back to your question, it's attracting a lot of really great students into the field, because they can feel this happening in the lifetime of their PhD, in the lifetime of their early research, and saying, I helped make that happen, be there at the very birth of this whole industry. Or not, we shall see. It is unpredictable.
Okay, we have time for maybe one more question. Go ahead.
I had a question, given our location here in Silicon Valley, the GSB. What's your thought on the role of venture capital and this kind of entrepreneurial spirit in this? I know that people got really excited after .com, well, I guess the good parts of that, and then also got really excited about renewable energy. And then they got really scared because the capital costs and timelines were too long. And this seems like even a magnitude greater on both those fronts. Is there any role at all, or is this really the realm of academics, government institutions, and massive utilities?
Well, clean tech is a wide field, and there are a lot, and I've been investing in it for a number of years. And from the get-go, because of my background, I knew inherently that there are a number of areas that you don't go, that do take a minimum of $100 million in 10 years. That's not a venture investment. A venture investment is something you can turn around in maybe 3 or 4 years, maybe 6 or 7 at the most, and then you might put 25 million into it over that period. So it's not a venture investable kind of thing, those types of technologies. But there are a lot of other technologies related. You've heard about the smart grid. That's really internet-based, computer-based technology, telecom technology overlaid on top of the hard grid, the transmission system, and the distribution systems. So though there's a number of plays there on how to use energy more efficiently that are basically software plays or are telecom-related kinds of things. And those are very venture investable. Those can make money and they'll turn around in the right time frame and so on. But if you're going to try to develop a brand new biofuel out of enzymes or whatever, that's a huge chemistry development chemical development kind of a program, and that's probably going to take a long time and a lot of money to develop something fundamental, a new biofuel of some kind. And that's been the experience. So people have gone into those things, have either given up on it or they have to pass it off to a major corporation that can then take it to the next stage and do a demo or get DOE involved or whatever when you get up to that level. So I would say clean tech is an investable space to go into, but you have to be very careful and cherry pick and look at what you're doing. And if you just go into it blindly, like a lot of these VCs did around here 10 years ago, when they couldn't even spell clean tech, there were a lot of bad investments made, and they're sitting on those things today, and they're not going to succeed at those. So you got to be. The answer is yes, but you got to be smart about how you pick them.
I would just add one thing to that, if I may. If it can be done, and in some cases it can, in some cases not. If you can rely on a technology which is not unique to your own solution space, I guess a biomass with a particular enzyme, that's unique to you. You've either got to invest in it and it works or it doesn't. If you have a logical solution in which you're relying on other people's industries and markets and sectors, which you can then piggyback from, then you have a potential way forward in which you can make use of private investment. Probably not venture capital investment, but there is a lot of long-term equity investment out there also. In the sense, so from our perspective, for example, we do not want to be driving the semiconductor industry. The semiconductor laser diodes happen to be the heart of all our systems. We want that to be driven by the television industry, by the lighting industry in terms of how to develop next generation diodes, and then leverage off that in the same way that we leveraged off the government in terms of its defence spending, and put that together in a package that then can be taken to market through private sources rather than having to rely on yet more government funding, which, surprise, surprise, is probably not going to be around in any significant amount. So I think there are solutions out there. You just have to be a bit more clever about it than saying, I've got a great idea and turn to a VC firm to fund. You have to leverage, and you have to pick a portfolio that is consistent with your time horizon. And we've actually been genuinely very surprised about the degree to which there is private capital out there that is willing to take a longer term view than you might traditionally.
We actually looked at an investment in a nuclear technology company back about 4 to 5 years ago. We didn't at the end make the investment, but a number of VCs did, and they continued to fund it. It's a plasma fusion technology out of the USC. And to my knowledge, it hasn't gone compared, so that and made money. So there are, and there are a number of other nuclear technology companies that have taken venture money, and none of them that I know of have succeeded today. So even in the nuclear field, if you take clean tech and include nuclear energy in that, there are investments there as well that venture money.
Okay, well, I think we have heard an excellent exposition of what the issues are with respect to nuclear power from our three experts here. I'm reminded that the first power reactor is now, came into being more than 50 years ago, and so for 50 years we've been talking about safety and cost and regulation and nuclear waste and so forth. And I think the idea is that if we're not going to continue to, if we continue to talk about them, if we haven't resolved at least some of them within the next 50 years, then nuclear's future is not going to be well assured. The hope is that they will be somehow resolved, and that we will have indeed a reasonable energy future that will enable the United States to continue to raise its level of prosperity. So with that, let's thank the three panelists, and then this will end the forum.